I hope that everybody's seeing me now. And well, hello everybody. Welcome to StanCon 2020. It's unfortunate that we have COVID upon us and we have to do all this virtual, but you know, given the circumstances, this is a fantastic conference. And so thank you everybody who is participating. You know, this is a global event that has been going for a few hours now. Total of 330 people registered, which is so awesome. Thank you so much. We're so overwhelmed, but you know, the support and the nice words from about 40 countries. So place the country where you're from in the chat. We'd love to hear that. We awarded 35 scholarships to attendees from about 18 countries, and you know, we really thank a lot of people, including the stand development and key contributors. And this event was really possible by the generous gift of 4 of our sponsors. So Metrum Research Group, and you will see the logos in the floor plan. Sorry, Jumping Rivers, Hoxo, and General. So which is sorry, I'm just like reading chats here. So Metrum Research Group was established in 2004 and is a global leader in biomedical modeling and simulation. Metrum has provided strategic support and decision-making for over 200 companies across more than 700 projects. And Metrum Research Group supports their clients advancing drug development programs by supplying them with the highest quality scientific expertise. Jumping Rivers is a UK consultancy company. Their services include training, infrastructure, step up, and modeling. Their consultants come from over 40 years combined of experience in Stan, R, Python, Scala, and other programming languages. Hoxo is a Japanese-based company and consultancy that supports all customers who wish to utilize data through state-of-the-art academic research and advanced implementation so that the clients can quickly and accurately make decisions based on their data. And finally, General, and we have a few folks from General in the conference, so thank you, Eric, Jackie, Dan. And General is working on improving success rates on oncology clinical trials. The General platform platform makes well-calibrated predictions of treatment efficacy from early clinical data, including patient-level longitudinal tumor measurements, status of key mutations, and other patient-level information. The models were trained on over 6,000 patient records of cytotoxic, growth inhibitor, and IO drugs and combinations. Also, this event is possible thanks to Kinetics team and Sally, who've done an incredible job handling all the logistics in such a short notice with very complex logistics and due dates. Also, just a reminder that we'll be enforcing our code of conduct, so we really ask you to be good to each other, otherwise I'll be watching you. No, not really, but you know, be kind and polite, especially with your questions and with your comments. Also, some etiquette for the event. We'll be discussing the talks for 9 minutes, so please do send your questions on the chat and the Q&A. So we have a couple of general chat and then Q&A. So please send the questions for the speakers on the Q&A. Also, you will see a lot of tables on the floor plan. If you see 6 people in the same table, generally somebody else cannot join the conversation. So we'll ask you to join a table and leave at least one seat open so that, you know, things flow easily. And also maybe during the keynote speaker, I will ask you to include a photo in your avatar because it might be easier to find you. Generally, Remo defaults to your initials, so it will be easier to find you if you have your photo or some like distinctive image. And lastly, StanCon 2021, hopefully COVID is no longer a thing by then, but the university, the Oregon State University have offered their venues, and hopefully will be hosted in the West Coast as we originally planned for this year. And we hope to see you there. And with that, the following part of the program will be introducing you to the 6 pitches of, it's not so much pitches, but it's just a summary of the talks that we'll have during the session.
Hi, my name is Cristina Barber, and I'm a PhD student at Boise State University, and I'm going to talk about how to fit plant-neighbor interaction models in the STAN. The interactions between neighboring plants have effect on their growth, survival, and recruitment. Managing these kind of interactions is key for restoration, for forestry, and for agriculture. It goes from knowing how much do we have to thin a dense stand to knowing which plants do we need to grow if we want to facilitate other plants. If we want to know the effect of these interactions on the demography, we need to use statistics. And actually these statistics could greatly benefit from STAN, its efficiency, and its assessment model tools. So the objective of this talk is to serve as a guidelines to fit these kind of models, plant-neighbor interaction models, and we will be touching base on things like solving the efficiency from sparse pairwise matrices typical from these kind of models, and how to include random effects.
Hello everyone, my talk is about categorical ratings. These arise in many contexts, for example in medical imaging. Here's a photo of a skin texture pattern, which we need to categorize into one of several predefined categories. This is done by trained experts who will look at each image and make a judgment on what the right category is. Now, if we have a series of such ratings, we can then have a data set like this, where we have multiple ratings per image. We can now use a statistical model to, for example, come up with a better prediction of what the right category is. An example of such a model is the Darwinian Scheme model. In our talk, we compare this model to a few other approaches, some of which are related to that model, and we assess when they do well and when they don't do so well. I'd like to also let you know that all of these methods are implemented in an R package called Rata, which is available from GitHub. See you at our talk.
Hello everyone, welcome to the teaser for ArviZ talk at StanCon 2020. We'll start with a super quick overview of the talk. First, we'll cover the motivation behind ArviZ and InferenceData. Then we'll show some examples of what they are and how they can help you. And eventually, we'll finish with ArviZ's role within the community. ArviZ aims to simplify the steps of the Bayesian workflow that fall outside the scope of PPLs, here shown in blue. To do so, it proposes InferenceData, a labeled data structure based on NetCDF to store from posterior to prior predictive to observed data in a single place. We therefore can use ArviZ for posterior exploration or prior predictive checks using only the data stored in this InferenceData object. ArviZ is a new package, it's still in beta. We welcome contributions and we are open about its limitations. So if any of this sounds interesting, go check the whole talk. That thanks to our international community, it's available in all these languages that you can see here.
Hey there everyone. In case you missed the full presentation of our talk on Orbit, here's a brief recap. My teammates, Jishi and Edwin, and I are working on open sourcing a Python package called Orbit. Orbit is a package for Bayesian time series modeling and forecasting, using STAN at its core for inference. We use Orbit at Uber on the marketing data science team to estimate media mix models to measure the impact of marketing levers, and then use the model to perform optimization in future time periods. A model meant for inference in future periods requires robust estimates and also the ability to reasonably constrain the parameter estimates. We also designed this package so that the top-level Orbit interface is simple and familiar to people that have been exposed to other high-level stats and ML Python packages. while modularizing the model math so we can simply extend in the future to new model cases.
Hi, I'm Brian, and I'll be talking about how to effortlessly compute frequentist covariances of posterior expectations in STAN. Now, why would you care about frequentist variances? One reason is that a mismatch between the Bayesian posterior and frequentist covariance indicates model misspecification and inaccurate posterior uncertainty estimates. For example, let's look at the posterior on this simple linear regression parameter on some simulated data from a misspecified model. Here's the Bayesian posterior, and here's the bootstrap distribution of the expectation. As you can see, the two variances are substantially different from one another because of the misspecification. Now, people rarely bootstrap the posterior because to compute the bootstrap, you need hundreds of additional MCMC runs, which can be quite expensive. We'll present a method called the Infinitesimal Jackknife, which matches the bootstrap closely, but can be computed with only a few lines of our code and no additional MCMC runs. In my presentation, I'll talk about this example, how to compute the estimator yourself, a very little bit of theory, and the results of some extensive experiments on the STAN example datasets. I hope you'll find it useful.
And those are our speakers. And now I have the pleasure of introducing one of my good friends and a very, very smart person, David Shor. If he's available, I'd like to bring him into view, and I can introduce him shortly. But David, he worked in the, like I probably don't need a huge introduction. He's very well known, but David worked in the 2012 Obama campaign and developed their election forecasting system. He spent the last 8 years at CIVIS as the Director of Political Data Science, leading the work on modeling and forecasting. And most importantly, pre-COVID, David was my disco buddy. So I hope that we get to do that sometime in the future, David. And with that, I'll leave you to your talk.
Thanks so much. It's a big honor to actually do this. We've been using STAN for a lot of our work for the previous. Hold on, let me just set this up. All right, I assume everyone can see this. Let me know if you run into any issues. But yeah, so this is about data science, U.S. politics, and STAN. At a high level, we're just going to talk about some of the methods that the campaigns actually are, and how it's actually done. So first, where I'm coming from, as Sue brought up, I came out of the Obama 12 analytics team, commonly known as the CAVE. This talk is really mainly I no longer work at CIVIS, but I was there for the previous 7 years, and I worked with some amazing people. So I'm just gonna basically talk through a lot of their accomplishments and sell how awesome they are. So just, in terms of what we did, our clients, we're basically, I guess, like the IBM of progressive data science. We work with almost every major political group, one way or the other. We worked with every single presidential primary campaign, except for Tulsi Gabbard, which was a little bit awkward. We worked with most of the party committees, the super PACs, outside groups, Planned Parenthood, labor union, basically all of them use us one way or the other. So in terms of what we actually do, it's election forecasting, resource allocation, predictive modeling, content testing. What this means is that we've conducted thousands of RCTs on literally millions of people. I think, in the last month alone, we've tested hundreds of different pieces of content. We've allocated over the last couple of cycles, probably billions of dollars, but every cycle, hundreds of millions of dollars for media spend. And we forecast every single House, Senate, governor, presidential, and ballot measure race in the country. Maybe not every single ballot measure race, but a lot of them. And then we score, I think, literally billions of rows per day. We really kill a lot of electrons. So in terms of the team, or my former team, just based in New York, 4 machine learning engineers, 3 data scientists, 2 Bayesian statisticians, 2 software engineers, 2 former White House staffers who know how to write SQL. So then, just in terms of how we think about things, we have a very, I think, boring and unromantic view of campaigns, which is that campaigns really come down to 3 basic questions, which is what races are close and where should I spend my money? What messaging should you base your campaign on, and what creatives work and don't work? And then once you decide what races you're going to invest in and what message you're going to have. How do you actually target and decide who should get your interventions? And so, coming out of 2016, we did a lot of soul searching and came to the conclusion that most of the traditional techniques here were really fundamentally broken. Just to go through them one by one, survey response rates are a lot lower than they used to be. And so survey research, the polling was wrong in 2016. And, this is, basically a lot of the traditional measurement methods no longer work. The second piece is that up until very recently, basically no content or messages that campaigns produced were rigorously tested, which is which is wild. And the last thing is that traditional voter targeting kind of came out of this like field and mail world and wasn't really very well optimized for like the actual interventions that campaigns put 80% of their budget toward. So just to go through these one by one, first, when you need to decide what races are close and where to spend your money, I want to explain this graph for a second. So the idea here is these states are rank ordered by how close they were, by basically how Democratic they voted in 2016. And these bars represent net spending by each party by electoral vote. And so in resource allocation, there's this concept of the tipping point state. Overall, Hillary Clinton got about 51.1% of the two-way vote. And in the state that ended up deciding the election, Wisconsin, she got 49.6% of the vote. And what we can see here is that even though the Clinton campaign had roughly 3 times more money than the Trump campaign, Donald Trump substantially outspent her in the race that ended up deciding the election. This is probably, the largest analytics failure that's happened, in American political history. You might have to go back to Williams, Jennings, Bryan skipping Ohio in 1896. But otherwise, it's kind of a big deal. And so the question is, why did this happen? And there's 2 parts. The first is that surveys underestimated our vote share, and Democratic vote share in Wisconsin and a bunch of other states in the Midwest. And that happened. The polls were wrong, both because basically response rates got a lot lower. When I started in 2012, survey response rates were about 12%. Flash forward even just 8 years later, 4 years later, and the percentage of people who were answering these things plummeted. There's like a lot of reasons for that. Robodialing became very popular. Do not call lists became more popular. Bill collectors have become a big issue. And so it's just no longer true that you can go and dial a bunch of people and hope and get people and then get survey responses that are exchangeable with the rest of the population. So just to talk about that a little bit more, all surveys are built on this assumption that controlling for what you're waiting on, or controlling for age or race or gender or anything like that, the people who are answering the phone are exchangeable with the people who aren't. And we have a lot of reasons to think that that's no longer true. Which means that we have to control for more things. And if you control for more things, then traditional weighting techniques kind of fail the curse of dimensionality. The second piece for why more money wasn't spent in Wisconsin is something that we really noticed in both 2016 and earlier, is that when you give decision makers election forecasts, they don't always respond optimally. You'll see, I think in 2016, when we went from 49 in Ohio to 46, people were like, oh, we need to put more money in. People would say phrases like, we need to give Marco Rubio a bloody nose. And these are important decisions, and it's good to approach them quantitatively. So the other thing I'd say is that in 2018, Democrats won, and polls said that Democrats would win. But underneath that, basically all of the polling errors that existed in 2016 were still there. Public pollsters underestimated Democratic support in these areas that swung toward him in 2016, and overestimated support, in the reverse. So a lot of people might not realize that these problems are still there, but they absolutely are still there. The second piece is content testing. Like I said before, up until 2018, there was basically no large-scale testing of content. We tested over 200 ads in 2018 for Senate and House races, and found that roughly 20% of them make people more likely to vote for Republicans. So one really underrated theory of change is just identify those ads and don't show them to people. Something that I think was really fun about this is just that in general, the more that people in the office liked the ad, the worse it did. And the reasons for that can be kind of clear. The people who work in political campaigns are young, they live in cities, they're disproportionately white, and they're probably not the right people to try to persuade rural white people in the Midwest or young people of color. This is one of the reasons I'm very excited about actually getting to do this kind of content testing at scale is, it's allowed us to kind of elevate ourselves a little bit from some of the biases that are, inherent in political staffing. So big picture, in terms of what we actually do, we survey tons of people. I think we, for a lot of our training sets, we'll have 1.5 to 2 million rows. We then join them to voter files and commercial appends and first-party data, and then we score the voter file. And so, we do this operation where we're fitting models with, 1 million or 1.5 million rows, and then scoring 300 million rows, and that's like the bread and butter of what we do. And there we go. So why is this hard? Basically the first reason is that politics and I guess social science in general has a lot of structure. Voting is driven by there's like a intersectionality in voting where ethnicity and socioeconomic class and religion are all complicated, complicated things that work with each other in complicated ways, and those interactions spill out into political behavior. But the exact way in which it works can vary tremendously from election by geography and also over time. Another side of this is that surveys are expensive. And so, because of, we really do have to cut things and cut the data up across time or space or state or district, but we have to do that in a really intelligent way because we can't afford to survey 500 people in every state ledge district or 5,000 people in every state ledge district. The other big problem is that our data is really biased. As I alluded to earlier, people who take surveys are really, really weird. And we both, have to do a lot of modeling and also control for a much wider range of covariates than other pollsters do in order to get accurate estimates from the public. And then, the last piece is that our business decisions are very sensitive to autocorrelated error. And so what I mean by that is that, ultimately, if we're modeling who you're going to vote for a House, the AUC of that model ultimately doesn't affect, the objective functions that we care about, because our goal is that we're scoring the file and we're using this to figure out which districts should we actually invest in, or what ad should we pick. And so if there's something weird about, West Virginia 3rd, which was a very competitive district last cycle, and we don't appropriately, regularize a party registration by state, random mixed slope term, then we can actually misallocate millions of dollars, which is something that, we've seen happen on the Republican side. And the last piece is that time effects, like changes over time, subgroup movements over time are very small. I think they explain, most of the variance in your data is explained by these main effects, but understanding these time interactions is very important because, ultimately in 2012, we got 51.9% of the vote. And in 2016, we got 51.1. It's only a 0.8% change over 6 years, but obviously the consequences of that were quite large. And so we have to do a lot of work to estimate very small effects. And so just to talk through what I mean by expanded covariates, one of the core reasons we think that public pollsters underestimated Clinton support or underestimated Trump support in 2016, and particularly did this in these Midwestern low education states, was this concept of social trust. So in the general social survey every 2 years, the government asks this question, which is, do you think that people can generally be trusted, or do you think that people should keep to themselves? And unsurprisingly, it turns out that people who trust their neighbors and have faith in society are substantially more likely to answer phone surveys. It's like I think an odds ratio of like 3, even controlling for controlling for covariates. And so, this had a lot of real consequences where even controlling for race or education, we were serving this high trust segment of the electorate, which did swing toward Clinton, but not this missing mass of voters who did not trust their neighbors or institutions. And this is one way in which survey takers are weird. We discover new ways that survey takers are weird every day. In the context of the U.S., LGBT identifying men are substantially more likely to answer surveys. Jewish people are more likely to answer surveys. The number of ways that survey takers can be weird is pretty large. And what's interesting about 2016 is that this bias has always been there. People with high levels of social trust were always more likely to answer surveys. But in the context of 2016, in 2012. Controlling for race and education and all these other things, social trust wasn't correlated with who you were voting for. But then in 2016, there was this change in salience where suddenly the 2016 election was much more of a referendum on whether or not you believe in institutions and less about whether or not you wanted universal healthcare. And so that's something that's really scary about this whole industry, is that you can have a method that can work because your exchangeability assumption holds on the on the covariates you're controlling for, but then suddenly there can be a change in the political system or a change in how people vote, and suddenly your methods can be wrong again. It's something that fills me with terror. So just I mentioned the deep interaction that politics has a lot of structure, and I just wanted to walk through this big table just to explain all of the weird interplay between race and religiosity and education. There's, I could probably talk about this table for hours, but there's a lot of really interesting things going on here. The first is that among white people, something that's pretty clear is that people who when we look at religiosity, we use the GSS's definition. We look at attitudes toward the Bible. So the three options are saying that the Bible is the literal word of God, the inspired word of God, or a book of fables written by man. It does, I think, it does a better job of predicting partisanship than church attendance or some of the other measures that people use. And something that you see is that for white people, saying that the Bible is a book of fables is generally associated with, has very large effects in a pro-democratic direction. People who aren't religious are substantially more democratic than people who are. With African Americans, there's a lot less spread, but the sign is completely flipped. In general, African Americans who are secular are actually more Republican than African Americans who hold literalist biblical beliefs, and that's that's a really interesting consequence of the role that Black churches play in the Black community and in politics, and it's a great reflection of how all of these models that we fit in all of these interactions correspond to real political and social sources. And it's something that really makes me love this job, is you get to learn a lot about, you have to think a lot about history and learn a lot about history. So just to go through some other interactions that are pretty important in here, something, if you notice at the top, is that generally having a college degree among white people is associated with large increases in your chance of being a Democrat. But among very religious people, having a higher college degree it actually has a negative effect. And it's because in general, educated people have more coherence. And so if you have a college degree, you kind of know that if you have a literal attitude toward the Bible, that you're supposed to be a Republican. And then the last piece, that I'll highlight, again, there's really a lot to talk about here, is the difference between how you vote and ideology. In general, Black, even though roughly 95% of African Americans voted for Hillary Clinton, less than roughly 40% of them, if you post-stratify the cells, identify as liberal, or it's actually 30% identify as liberal. While for white Democrats, it's probably something like 70 or 80%. And so, all these concepts, ideology, race, religiosity, education, they all interplay with each other in a lot of ways. And these deep interactions are actually very important if you want to understand targeting or history or why people do what they do. Another example here of interactions and partial pooling is here we're looking at 2016 vote share by administrative party registration and Senate vote share. So just for people who aren't in the US, generally in the US, in most states or in roughly half of states, when you register to vote, you tell the government what party you identify as, and then that is used for participation in state-run party primaries. And so, what you can, and this is administrative data that we have and we weight by and model with, but something that you see is, in West Virginia, even though Hillary Clinton got about 27% of the vote in West Virginia, there are still more registered Democrats than registered Republicans. And the reason for that is that 20, 30 years ago, West Virginia was a very Democratic state. Since then, it's become extremely Republican. But because people only change their party registration when they move, there's still an enormous lag in the actual numbers. And so, what you can see here is that just looking at the Clinton 2016 column, Democrats get 84% of the vote of registered Democrats in Florida, but only 47% of the vote of registered Democrats in West Virginia. And so if you were doing partial pooling and didn't pool in the correct way, you would really get West Virginia wrong, and that would be a pretty big deal. But then the other thing I think that's really interesting, and this gets to how a lot of politics is still local, is that there was a Senate race in West Virginia in 2018, and even though Hillary Clinton only got 47% of the vote among registered Democrats, Joe Manchin, who was running for Senate, got 78% of the vote. And that gets at some of the historical complications where a lot of these when you look at the Senate Democrat column, some of these state effects are actually smaller in some ways, because a lot of these former Democrats, these people who they were coal miners and they identified with Democrats their whole lives, they hated Hillary Clinton. They probably also don't like Joe Biden, but Joe Manchin, he's like a good old boy. They remember him from the 90s, and they remember when he was governor, and they were still willing to pull the trigger for him. And so there's a lot of weird local stuff like this. One of the downsides, I think, of federalism in the US is that there are just tons of elections. There's something like 4,000 state legislative races, 435 House races, 30 Senate races, and a presidential race, all these ballot measures. And people actually do somehow manage to hold pretty intricate opinions about all of this stuff. And so, if you want to build power, it's very important to take all of this stuff into account. The last piece, another piece is that, as I mentioned before, time effects are usually very small. Usually public opinion is very stable. So here we have a poll. Here's a graph showing the Obama campaign's election forecasting, which was, I think we surveyed about 1.2 million people over this time period, and comparing that with the running Gallup tracker. And the first thing is that our data was much more stable, both because we were able to control for differential non-response bias because we had administrative data that we were modeling with, and then also because we surveyed a lot more people. So the Gallup line moves around a lot, and it's just important to realize that most changes, I think if you calculate it out, actual changes in public opinion explain something like 1 or 2% of the variance in public polls, with the rest being either differential, bias or sampling error. But the flip side of this is that if you aren't, the previous slide shows that regularizing across time is very powerful. But then the flip side is that sometimes things actually change. So, here's our primary polling between Nevada and Super Tuesday in the Democratic primary. And basically what we saw in our surveys was up until this point, over the previous week, public opinion had moved at maybe a 1/10 of a point, or it was maybe 1/3 of a point per day. But after Joe Biden won South Carolina, Joe Biden's support increased by 26% over the course of 3 days. And so we had pretty high frequency polling, and we could actually see that he was increasing at roughly 1/3 of a point per hour. And so if you don't have proper stochastic volatility models, then you're just going to regularize that all away. And so it's a big difficulty of our job is, we want to absorb power from the fact that things are usually very static, but then sometimes there are regime shifts and we need to have that not break our systems. So then, we do all this work and there's a question of like, does this actually help? And I think the answer is yes. So, here's just a summary of some of our election forecasting results compared to 538 and other organizations in the 2018 midterms and the 2020 primary. When you look at the 2018 midterms, we had roughly 40 to 50% less lower mean absolute error than 538. Our September 1st forecasts were substantially better than their election night forecasts. And in 2020, if you compare to some other groups, we also, I think, did a much better job at comparing things across states. This accuracy, having a mean absolute error drop by 40% doesn't sound like much, but it has very real resource allocation implications. If you go through and calculate the decision theoretic implications of being able to target better, it really ends up being quite large. One concrete example here that's masked by the averages is that going into 2018, we all of the public polling, because of the biases that I had talked about before, had the West Virginia Senate race as a very D-leaning race. I think the 538 average was something like D+11 or something like that. And as a result, generally, a lot of organizations in the Democratic Party wanted to pull out of West Virginia and put money into closer races. But because we did all of this stuff, I think we had the West Virginia Senate race at like 50.3, and I think the final result was 50.4. And I think there's like a really clear story that had our polling been different, we wouldn't have invested money. The other side was putting money in, and I think there's a clear pathway to us losing the state. So like, these improvements I think really are worth all of the effort. And so just in terms of challenges for data science and politics, the first thing is that when we actually talk to our clients, which are generally older people who run some of these large electoral groups, most of them lack social science background, and they ask a lot of questions that don't have clear, straightforward answers. This is like in general a problem with social science, where everything we do is a mix of sociology and politics and history, and there's not actually a way to directly map a lot of these questions into an experiment or into a model. And so sometimes you have to take some leaps of faith. You have to say, oh, I'm doing this big conjoint, and this conjoint really should inform how we're going to do a speech. And so it's always really tempting to focus on these very well-defined problems, like how do you target mail, or how do you, do fundraising. But, we found that most of the impact is in helping, with these fuzzy questions. The way that, I think about things is that, we talk to these decision makers in the Democratic Party, and they make decisions like, how should we talk about immigration, or what position should we take on, whatever just happened. And they're going to make the right decision maybe 70% of the time. And if we can figure out how to increase that to 75, then that's just an incredibly important thing. The other thing is just that, again, these decisions are often impossible. The science behind any of these things is never going to be perfect. And so a big part of doing a big thing for me is just thinking about meta-analytic, like meta-heuristic processes. Like you can argue, and historically, like you'd have a room with like 12 people, and they'd argue for hours about what ad they should put up. And I think it's better. We think a lot about how do we set up processes that help kind of streamline this decision making. Like, oh, if you have an ad, let's test 4 ads. Let's generally use the one that's the best, that tests the best, or in the top 2. And we find that kind of this having automatic decision processes kind of avoids panic and jerkiness, and it's a good practice. And then the last piece is that very few of the people that we work with have a background in social science or statistics. I think literally none of them. But my experience is that it's very easy, especially as a quantitative person, and I'm as someone in my 20s, to kind of roll your eyes at the pointy-haired bosses. And but in my experience, in general, whenever the data people have disagreed with the old school consultants have been right maybe like 80% of the time. I think a lot of my career arc in the last last 8 years has been slowly learning that a lot of the people I hated in 2012 were actually right about most things. And so you should ignore people with a lot of experience at their peril, at your own peril. So now talk about Stan. So it brings me an enormous amount of personal pride that all of our production models are Bayesian. All of our time series tools are fully in Stan. If you actually go back to the old Google group, Stan user group, you'll find me asking questions, I think, 1 week after Stan's creation in the summer of 2012, because we were using OpenBugs back then, and I was very, very eager to stop using OpenBugs. And the last piece is our individual modeling is, approximate phase. It's all done with variational inference and TensorFlow probability. Our data sets are generally too large, given our time constraints, to make using Stan directly feasible, but it would, hopefully that changes soon. Generally, we have because we update everything every day, generally our models, a lot of models will feed into other models, so we want to keep everything under 2 hours. And generally, they'll often have more than 1 million rows. Using variational inference has been a real journey. It does not work out of the box. We've had to pull from the normalizing flows literature in order to get reasonable results. The basic issue, if you want to fit multi-level models in Stan, is variational inference kind of assumes that all of your posteriors are independent of each other. And if you think about it, if you have a regularization parameter like the hyperprior of your distribution, the size of all of your coefficients is actually going to just be literally proportional to that thing. And so if you don't take that into account, you will regularize everything incorrectly, which is really bad. So I think it's been an interesting journey, just because I think that very few people in the ML or TensorFlow community really think a lot about the kind of models that people try to fit in Stan. With these, I think we came to it because something that's unusual about us is that we really cut in a lot of ways across time, across space, across districts. And we really want to make sure that we're doing it exactly to the right amount, which means we can't grid search over our regularization parameters because we have like 100 of them. And so that's something that has been a little bit unusual. And it's really been a real struggle to get this to work. But and so just the last piece, for how we use Stan is that basically, if anyone here has ever used variational inference, I think a solid half of the time when you try to use it, it doesn't work. And so Stan has been extremely helpful just in terms of checking whether or not these things work. We have an elaborate system of Oracle tests that to double check all of our layers, our TensorFlow layers that we use in Stan. All right, so that's it. Do you have any questions?
David, that was fabulous. And there are definitely some questions in the chat, and I have also a few of them. But if you want to just stop maybe sharing your screen so that people can see you better. But I'm just going to read the questions from, go straight to some of the questions, and then I have another. We'll see if we have enough time. We have the next 15 minutes for questions. So if you have more questions, please put them in the chat. So Max Livingston is asking, you talk a lot about determining where to spend money, but didn't get into what effect of the money is. And in that sense, is there any research that you guys have done on the marginal impact of money in these races?
Yes, that's a big part of what we do. When we do our resource allocation, the basic idea is that we have, first with our election forecasts, we generate, a bunch of simulations of the election. And then we have econometric models for various kinds of interventions, whether it's mail or knocking on doors or television or digital spending. And so we do a lot of work to try to econometrically estimate not just the effect of spend, but the decay effects of spend. What are the prices vary a lot over time. So, what's the effect of spending in September versus October? What's the effect of, the 100th ad you see versus the 10th ad that you see? And then what are the competitive dynamics? If, you're on the air and your opponent isn't on the air, how does that affect, your treatment effects? And, I'm not going to claim that we know exact answers to all of these questions. But, something that's a lot of this, we have to use a lot of non-experimental causal inference. We also do a lot of experiments. But, one thing that's hard is just, the effects of a lot of these interventions are very small. But because, like, advertising in general, I mean, there's the great paper on the impossibility of measuring the returns to digital advertising. There are a lot of, advertising is simultaneously ineffective, but also extremely cheap. Buying 1,000 ads costs about $30. And so if showing someone 10 ads had a, had a 0.1% effect, or if one ad impression had a 0.01% effect, it would still be one of the most cost-effective interventions out there. And so, yeah, we do our best to do a lot of this non-experimental causal inference and also mixed experiments. But I remember when we first started talking about doing this in 2015, I talked with, one of my coworkers, and she said, oh, I don't really buy the causal strategy, like you're instrumenting on price. I don't believe it. And then, we have this challenge where, we have to spend $200 million. So we have to do something. And it is very harrowing in that, the optimal allocation across states or across time is very sensitive. So whatever your assumptions are about decay or diminishing returns or competitive dynamics. And so we have to do the best we can, but there's always a lot of noise, and it's something that's stressful about the whole thing.
For sure. And like, I used to work in programmatic advertising, so it could be incredibly cheap. And I think Edwin had a very kind of tangential question to this topic, which is that previously, a lot of the campaigns were sort of offline in a way. And so now seems that a lot of the campaigns are focusing on online ads. And what are the advantages or challenges of such change?
Yeah, that's a great question. So, there's I'd say two big advantages of online advertising. The first is, I think, is that you can target online ads in ways that you really can't with television. There's a lot of ways to target ads, a pretty dizzying amount. If you have a list of persuadable voters, you can go and onboard them, even though first-party targeting is kind of a scam. Or you can do a lot of zip code targeting. You can do interest targeting. There's like a lot of options. And people vary in terms of how persuadable they are, and so that there's a lot of value there. But then I think the underrated part of targeting is that generally campaigns have access to administrative data on who's voted in the past and who isn't. It's actually publicly available. Whether or not you vote is a matter of public record and relatively easy to look up. So tell your friends, all of you should vote. Otherwise, you might get shamed for it. But this, in general, persuading someone who isn't going to vote doesn't matter. And so that drives a lot of the heterogeneity. Like, a lot of campaigns, particularly in primaries, are like really insistent on being able to restrict their spending to people who are likely to vote. But then the second piece is a little bit more obscure, which is television spend generally most of it goes through these geographies called designated media markets. There's about 312 designated media markets, which in general cross state lines and kind of roughly represent commuting zones or metropolitan areas. This makes resource allocation very challenging insofar as if you want to advertise in New Hampshire, roughly 60% of New Hampshire is covered by the Boston media market, which means that you have to show your ads to every single person in Boston. This actually makes New Hampshire the most expensive state in the country to advertise in. Wyoming actually has some similar problems. You have to show ads to Salt Lake City and Denver and a bunch of other groups if you want to cover. And so then you get into all kinds of weird, intricate stuff. Like, there's this one cable station in New Hampshire called WMUR, which is the only way to advertise and they end up making tons of money. Las Vegas media stations. That really, our whole political system is like a redistribution of wealth to local media news stations in swing states. But then the risks of digital advertising, so the advantage is that with digital advertising, you can target by zip code and you could totally avoid all of this weird, intricate Byzantine stuff. The disadvantages are that it's very hard to test, what's the advantage of, there's so many different ways to buy digital ads. When you have video, you have skippable video, you have, non-skippable video. You have these Facebook videos where it's like muted by default. And so it's very hard to actually know the relative effectiveness of all of this stuff. And I'm not gonna pretend I do. At this point, I think we have a pretty good idea of what is the effect of digital overall, but actually breaking it all out is very difficult. And generally, the other last piece about digital that makes it hard is that generally in politics, this is like kind of the core measurement problem in politics. We don't observe our own conversions. If someone sees an ad and decides to become a Democrat, we have no way of knowing. There's no like tracking pixel in their brain. And it's a real issue because the only thing we do get is engagement metrics. And the problem is that only very engaged voters engage with, like only people who are very likely to vote engage with political content. How many likes a YouTube ad gets is like often anti-correlated with how effective it is among marginal voters. And so that really, it becomes all the ad tech tools aren't really built for us, which makes it hard.
Sure. And is there any way to say correlate the number, like if you're able to target by zip code, could you sort of correlate the convergence at the zip code level, given that you have voter registration, I guess?
Yeah, so what we end up doing is, we test content. We do a lot of randomized controlled field experiments, which are very, either field experiments or in-survey experiments, which is like very complicated. We've set it up at this point where if a campaign wants to test an ad, they can send it to us, and within 24 hours for like a couple $1,000s, we can not just tell them the effects of the ads, but the heterogeneous effects of those ads by zip code or by demographic or by media market or, Fox News versus CNN. And so we've done a lot of work, but it's been really logistically challenging. Dollars, I wish I was Dollar Shave Club or something so that I would just know who clicked. Having to survey people is very annoying. For sure.
There's a bunch of questions that we have in the chat, and just please keep them coming. If I don't get through all of them, I'm sure that you can find David in the tables. But Zachary is asking, what do you use to specify priors on correlation structures in STAN? Are LKJ priors precise enough to pick up on West Virginia type nuances?
That is a great question. So we do our individual level modeling in TensorFlow probability, and it's like a real it's a real challenge. Like I think a lot of the traditional MRP modeling approaches were really designed for having you have 4 covariates and you want to interact them all with state or something. And once you have 500 covariates, then it becomes a real challenge. And so we've had to iterate, on a bunch of, like, how do you take the gains from regularization MRP and in a high dimensional setting and make it do it in a way that's like computationally feasible. And that's something that honestly we've iterated a lot on. And I think it's like a legitimately very hard problem. On the STAN side, one place where we do have correlation structure stuff is just in terms of time. In general, in a presidential race, how states move are extremely correlated, and that's really helpful. Like if you do a bunch of surveys in Florida and you see a downtick, that should tell you something about Wyoming, even though we don't have that many people in Wyoming. But then the flip side is that correlation isn't perfect. And there's also a deeper aspect of this. Like we might be down in Florida, but only because we're down with Latinos and with Hispanic voters. And there aren't any Hispanic voters in Wyoming. I think there's literally like 600 or something. And so, how do you properly parameterize, this kind of correlation structure? And we find like just trying to throw some covariance matrix out of the box, doesn't work very well. So we try to put a lot of structure in our models just because, ultimately we don't have that many weeks. There's a lot of covariates. And so there's like a lot of tricks we've had to do to get reasonable results.
For sure. And I think, so I might be able to do 1 or 2 more questions. what diagnostics do you use to validate variational inference runs?
That's a great question. So generally so there's two kinds of model validation, that we do. The first is, there's all of the great cross-validation stuff for seeing if there's all kinds of measures of cross-validation to see if your model works in a non-Bayesian context. But a big thing that we do, and I mentioned this in my slides, is that we do oracle testing in a way where instead of simulating fake data, where I think when you do that, a lot of the time it's very, whether or not your estimator works is very dependent on assumptions around your fake data. We run our models in Stan, and then also run our models in variational inference, and then in either subsets of the data, whether in column-wise or row-wise, and then see if basically if the confidence intervals are the same. Obviously you want the means to be the same too, but if you can get the first two moments to be the same, then, we feel like what we're doing works. In our experience, Stan, we trust that Stan works for Bayesian computation. And so that's how we test a lot of this approximate Bayes stuff.
Awesome. And I think the last question, basically, how does your personal political views affect your research?
That's a great question.
You have views.
Yeah, I think so. I think, it goes in both directions, where I think I like to tell people that, fundamentally the kind of work that, our team does, there's a lot of very cool math, and I think it's very impressive. But if you step back, the advice that we end up giving campaigns is that you should talk about popular things and not unpopular things. You should spend your money in states that are close and media markets that are cheap. In a lot of ways, it's not rocket science. Operationalizing it at scale in the context of the US political system is a challenging technical problem. But stepping back, the core problem in my industry is that everyone who works in politics is very ideologically motivated. It's why we're doing this. And that really pushes people, I think, to convince themselves that things that are kind of clearly dumb are not dumb. And those things can have an ideological valence, realizing that actually it's unlikely that, Bernie Sanders was going to mobilize a bunch of people, to get every young person to vote in Iowa, or realizing that maybe running ads on immigration in Wisconsin might have been a bad idea. A lot of these mistakes that get made. Sometimes they're made for statistical reasons, but a lot of times there's a lot of motivated thinking. And so I think it's really important, in our field to do our best to try to go where the data takes you, even if the conclusion can be a little bit unpleasant. But I think, the other side of things is that it is really helpful, on the other hand, to have a coherent theory of the world. You can't test everything, and you can't, it's impossible to test everything, and it's impossible to, fully quantify every kind of question. And so having an ideological superstructure for how you think the world works is really important for being able to actually make decisions or lead you in the right direction. And, I'm not going to talk about my own ideological beliefs, but I do think that they were very helpful in, in terms of guiding me to one line of inquiry being successful or another line not. It is useful to believe things.
And I think that sort of ends the Q&A section of this talk. So, David, thank you so much for being here. It's a pleasure to, chat to you as always. So if people have more questions, feel free. I believe that David might stick around for the rest of the conference. So feel free to visit his table and find him to ask your questions. And with that, I will now recap the talks that we're going to have again, and then we will follow with the discussions. And with that, if I can bring Cristina into view, that would be fantastic. And hey, Cristina, good to see you. And
hi,
so
good to see you too.
And for everybody in the chat, please place your questions. I have a couple of them, but if you're ready, so I have talk, please start placing the questions in the chat and I can read through them. But just to say that everybody, I've been getting a lot of offline comments like saying like, oh my God, her slides and her talk were amazing. Like, I think on top of that, you need to give us also a tutorial on like, how do you put such a beautiful presentation. And so, and with that, I want to start with a quick question on if you could elaborate a little bit on, or give us some examples on what metrics are generally used for positive and negative effects when studying plants.
Well, usually what you're looking for is metrics that can tell you about the growth, the survival, or the recruitment when you're trying to fit individual neighbor models based on the demographics. So, for example, for growth, you could measure the height of the trees or the DBH at the breast height and do that a couple of years. So, at least a couple of years. So, what is the change from one year to the other. If you can do it for more years, even better. For recruitment, for example, you can sample which are the individuals inside of a transect 1 year, then go back the next year to check how many new individuals are you getting there. And for survival, the same for recruitment, but instead of looking what is new is what is missing. So that is more or less some of the things that you could look at when you're measuring these kind of things.
That's fascinating. And in this sense also, what happens when you have, say, like ecosystems where plants are like very sparse, comes to mind like drier regions, what would you suggest? Like, would you suggest a different approach to the approach that you use in your video, or what would be a good way to go about it?
I think you can still use individual neighbor models, but it is true that maybe if they are too far, it might be harder to fit the models. And actually, one of the reasons why these species or these plants might be too sparse is because of these interactions that are building this like sparse structure. So maybe instead of like doing a model as I did, like maybe or in nature or something like that. In the second example, they use seed additions. So you can actually create your own kind of like crowded place to see how actually that structure that is sparse might be working because of these interactions. Or you could even have orchards or common gardens in which you can like model all of this and see what happens exactly. So like part of the question is also like, why is it sparse, and does neighbor interaction has something to do with this?
For sure. And we have now some questions coming through the chat, so I might jump into those ones. So Lizzie Wolkovich here says, given how noisy ecological data often is, for example, trying to relocate seedlings over time, have you added any observational process to your neighborhood models, or do you know of any work trying to do that?
So I have been working with observational data, and actually these two papers are based on observations. So they are based on data collected in the field. And also I'm working for my PhD also into a model that is also observational. So we have all these transects for recruitment, in which we measure recruitment, and then we link them with the parent trees on the landscape. So yeah, like the two papers that I have and I mentioned inside of the talk, both in 2012 and 2014, will be good examples of that.
I hope that's sort of where you were going, Elizabeth. If not, mind clarifying the question a little bit. Raul Peralta is asking, can you comment on what kind of co-founders might be present in your analysis?
What is co-founders?
When something is interacting with what you're trying to measure, but you don't, you need to account for it as well.
Yeah, so there are a lot of things that could be acting, for example, environmental variables. Also variability because of the landscape, like spatial variability. So you can also include those factors inside of the model, maybe not in the interaction kernel itself, but it can be part of the model. For example, in one of the models that we have this crowding effect included. That's kind of like part of the interactions, but it could be substituted by something that might be like an environmental factor or something like that. And also in the second model, we have the plot effect as a random effect. And that will be another way to controlling for these kind of like variability that you have in the landscape.
Makes sense. And again, keep your questions coming through the chat. This is actually a very similar question that I had from, I'm hoping that I say your name right, I'm sorry. Soyan, I thought that using segment function instead of a sparse matrix is very original work. And this person wants to know what was the motivation using this. And my question is, like, if you were not doing segment function, we use a sparse matrix only, or what other techniques are available for these sort of functions?
So the motivation is that there was a moment in my lab in which we were, like, all the co-authors inside of this talk having to fit huge databases with sparse matrices because we were talking about recruitment and interactions between plants. And we were discussing how hard it was to get the models in less than 2 days or something, like making it just to 1 day. So I think the motivation was more like a kind of like a need from all of us to find a way to make it more efficient.
And I think that was one of the functions that you basically used to choose the radius, if I'm interpreting things right. Is that correct? Like
can you say that again?
I think how fast the results you were getting was part of also like what was driving the diameter that you were choosing in your model. Is that right?
So the part of the radius is more to check that the efficiency of the segment is not just because we are having less data inside of the segment, but because it's actually more efficient than the matrix. The radius, you can choose them in different ways. You can put different of them and then fit different models and see which is the one that fits the best and explains better. Or you can even include the radius as a parameter inside of the model, and it will be estimated by the model. Yeah, like those could be ways. And I think we also asked which other ways I think that I could use instead of the segment function. And for example, I was thinking about the Laplace approximation from one of the talks that we had here in Stan, this is StanCon. And I think that that's pretty interesting. Someone in one talk that I had also suggested a QR decomposition of the matrix. But I haven't tried none of those, but I think those could be good candidates also to do these kind of things.
That's fascinating. We have an additional minute. So Yi is asking, what do you think of the effect of, what climate change and how that could affect your work in this case? Sorry, I think I didn't read the question quite correctly. So what do you think of the effect of range expansion due to climate change and how that would affect your work?
Well, I think it will be pretty interesting to look these kind of things because the plants are, like, some of the plants are expanding. They are getting, because of climate change, to other places. So knowing earlier what are going to be the interactions between the plants and in these expansions, like it will be something like the invasive species, I think, so that you want to know what is going to happen inside of the ecosystem if you're having these range expansions and things like that. So yeah, I think that's a way we could do that.
That's for sure. And Cristina, I think we ran out of time, but thank you so much for your talk. It's Mitzi Morris is like saying that she loved the slides as well. So thank you so much for being here. Next in line, we have Damjan, who I met in Australia. So Damjan is a professor at the University of Melbourne. And Damjan, welcome to StanCon. Thank you so much for being here. And I think you're muted.
Indeed, I am muted. Thanks, Sue. Yes, it is great to be here. I think Australia's quite far away, so having it online is just a really helpful way of getting us all together.
For sure. And Damjan, during your talk, you presented a new package that you're working with a couple of collaborators. Could you tell us a little bit what other models or modifications of the models you have included in this package?
Yes. So we have the two models that we present, the Dawid and Skene model and the class conditional one, which is the restriction. In addition, we've also implemented a hierarchical version, so a hierarchical Dawid and Skene. So all these models have actually been described elsewhere. So none of these are new models, but as far as I could see, no one's packaged them up somewhere where you could easily use them. So that was the motivation for us to actually create a package that gives access to these models in an easy to use piece of code with nice tools for visualizing the output and integrating it. So far, those are the three models. So they're actually all variants of the Dawid and Skene model.
That's incredible. And someone is teasing me here that now I suddenly sound a little bit Australian now. Well, it must be the 10 years that I spent there. Now, I have a question in the chat. So, Vish, I'm hoping that I'm saying your name correctly. Have you looked at the Netflix movie rating competition that was posted a similar problem? I don't know if you're familiar with this, Damjan.
Oh, I remember many years ago looking at it, and I can't remember all the details, but I think there was lots and lots of people, each rating movies. So yeah, so I guess it's similar setup. I think the ratings are like, let's say between 1 and 5, 1 star, 2 star. I think that's the right thing. I don't know if the prize there was for, I can't remember, was it for working out what I think you're predicting future ratings for each person. Is that right?
Yeah, I think that was similar. I think there were like several questions.
Yeah, so I don't know. So you may or may not have connections. Most of the problems we're interested in are similar to the one I presented, where we have, for example, medical images. So they're the focuses on getting the sort of the correct rating for each image. So each item has some sort of inherent truth that you're trying to get at. In Netflix, I think each person has their own truth, so it's sort of a harder problem. So it's not like everyone's trying to get the same truth. Everyone's got their own version, and then so it's probably more challenging.
For sure. And another question that is coming through the chat is quite interesting here. It says from Trevor, could you talk about the cost or benefits of using multivariate logistic normal versus Dirichlet in this type of analysis?
So that's a good question. So the results I've shown you are all using the Dirichlet formulation. So in the hierarchical version, then we switch to using the switch to like a logistic. Well, it's a multivariate formulation where multivariate normal underneath to allow partial pulling. So I didn't present any results of that one. I was hoping we could get those ready. In these problems here, there's label switching is an issue that needs to be dealt with. So I think there's just a bit more, it's a bit trickier so the benefit is that you can do things like partial pulling much more easily. The trick is just getting it running. So far we haven't run the hierarchical version for our particular simulation runs. We just need to sort out making it merge properly. And in this case, label switching is an issue. One thing that would help is if we did actually have observations that we could trust were sort of gold standard, like if we knew some items' actual ratings very, very precisely, But in general, the sort of problems we're working with, we don't have a notion of a gold standard, or it's very hard. Either we don't have it, or it's something that's very expensive, so you typically have it in practice. I think we can probably get the hierarchical one working in generally. We just have to sort of maybe tune the prior a bit more, so that's just a bit more investigation to work with.
For sure. And what sort of priors are you using for these models? Or is that, I guess, depending on the data?
So for the ones I've showed you, we've got the Richelet priors. And so, in fact, one of the things we've investigated is how to set these up in a way that works well and also is easy to understand. So the Darwinian Scheme model is actually one of the examples in the STAN manual, and there is a prior that's suggested there, and the prior is weakly informative, so it does put extra weight on the diagonal of these rater matrices. So we're assuming that our raters are reasonably accurate. So there's just a choice of how much weight you want to put on that. And so the way we've parameterized, the way we are suggesting is to parameterize it is a way that we can actually control those two different things. One is what's the sort of the accuracy you expect for your raters, and then how much weight to put on it. And that's essentially a reparameterization of what's in the STAN manual, but in a way that makes those two things independently settable. So for the priors we've used in our investigations, we tend to put in a mean accuracy of around 0.65 to 0.7, which is sort of similar to what we've been simulating. The one in the STAN manual happens to have it a bit stronger. It tends to implicitly around 0.8. And then you can also choose how informative or non-informative you want it. You can't really make it, you need to have it informative enough to let the model actually work, because otherwise you'll end up with these label switching problems and also poor convergence. So you need to regularize it enough. So in other words, you need to have it informative enough, priors need to be informative enough to make the model converge properly. And we have the one in the STAN manual is reasonably good, but we've just made it a little bit less informative and get a little bit better performance in our simulations when the reality is a bit further away from the truth. In other words, where the raters aren't quite as accurate as what you expect them to be. So that was sort of a long answer. I hope that makes sense.
For sure. And I think we might have time for one more question, and if we can walk through it as quickly as you can. So is there any, sorry, Martin is asking, is there anything in the Darwin Scheme model that you think it might be missing with the medical data?
Yeah, so the model, for example, doesn't have a notion of which treats all the items as exchangeable. So some items might be harder to rate than others, and also it also assumes that the raters are conditionally independent of each other given the truth. So some of them might be more similar to each other than the other ones. So the hierarchical model helps with that. It lets some information sharing between raters, but otherwise putting in a notion of item difficulty might be something that is possible. And I know that Bob Carpenter and colleagues are interested in this problem and have been working on it. So yeah, that's an extension that's definitely of interest.
Well, thank you so much. I think we're at time, but Damjan, thank you so much. I hope that it's not an ungodly hour in Australia. So thank you so much for being here at StanCon. And with that, I would like to bring into view Vianey, who is one of my co-chairs for the session and who will be basically handling, handling, that's probably the wrong word, but she will be the main person coordinating the following talks. So Vianey, if you are around, and if we are having technical issues, I'll be happy to maybe jump into the next discussion if Vianey is not online. Yes. Hey, Ravin, how are you?
I could just gonna drop you into this.
Yeah, fantastic. So thank you so much for being here. And, ArviZ, I have to note that you guys send your talks in different languages. So kudos. We're very excited to, to just have you all in the conference. So thank you so much for sending all these beautiful multilingual talks.
Yeah, thanks for making it happen.
And so I have, I'll be jumping here with a couple of questions, and some of the ones that we have are like, what are some fun examples of ArviZ used in practice?
Okay, let's see. Well, so so people are using it all over. I think I'll talk about mine. I use it at SpaceX, probably the coolest one, I think. So I use Bayesian theory to characterize supply chains for various companies. It was rockets. Now I work at Sweetgreen, so I use Bayesian data science for salad manufacturing. So that's my application of it. Alex Andor, who gave the French talk, he uses it for political forecasting, and so he's got a couple notebooks on that. And then Colin used it for flight analysis, but he also now works on TensorFlow probability team at Google, so he uses ArviZ with like TensorFlow probability. So I feel like all the folks in the core contributors, but then just in general, use it for whatever cool Bayesian problem they happen to be working on.
I guess at this stage, I should ask if you talk to Matthew at all to incorporate some uncertainty visualizations within ArviZ.
Yeah, so we definitely reached out to Matthew. Him and I are scheduled to talk at some point about whether he could put an InferenceData either method to like read in or read out on that. And I think Posterior had just opened an issue ticket yesterday that they're like, should we use InferenceData or not? So thanks for helping us get the word out there.
For sure. And a question through the chat. So Raul Peralta is asking, what are your thoughts on Bayesian model serialization, having something like an open format for Bayesian models?
So we think it'd be really cool. I'll point out ArviZ and InferenceData doesn't solve that particular problem right now, but for the whole idea of like open and reproducible science, it would be, I think everyone would appreciate if you take a Stan model and translate it to like MC3 or MC or NumPy or whatever, or vice versa, right? Like I think everyone in the Bayesian community is trying to do, good and rigorous statistics, and there's no reason a PPL should divide that by any means.
That's let me. There's more questions coming through the chat. Yi is asking, can you talk about the application to additive manufacturing?
Sure. So additive manufacturing, for many folks that don't know, is like, it's called 3D printing usually, but there's a whole actually class of these things. I feel like, so there's additive manufacturing and there's statistics, and you could use statistics with manufacturing in a ton of ways. So there's people that use statistics to do fundamental research on types of manufacturing methods that work maybe better or worse. So one of my friends at the University of Wisconsin-Madison is doing micro laser machining, and he uses statistics in like an academic sense. I use Bayesian statistics in industry. So for manufacturing, we're always trying to make sure everything fits together, which is a surprisingly hard problem. And no two things are ever alike, but they have to be alike enough that they can be mass manufactured. So statistics helps me characterize uncertainty in physical objects. Similar to like the plant growth talk, right? That's an example of growing a plant and seeing how plants affect each other. For me, it's like, how do manufacturing decisions affect the final product?
So just questions to the chat. Yeah, I think you're monopolizing the chat. So he mentions stress analysis in that application is nasty to solve. So I'm wondering how MCMC can be applied to it.
Let's see. So I think I wouldn't say MCMC. I just say statistics and Bayesian statistics in general is really good at characterizing uncertainty with a low number of samples. So like, for me in manufacturing, I'm sometimes jealous of the people at Google or Facebook. They get 1 million click events for like for quote unquote free. Like computers can churn and generate data like no other. But with manufacturing, I didn't have a million rockets. I couldn't really A/B test rockets. It's not like a thing that would work very well or be very economically viable. So Bayesian statistics in general, whether it was like conjugate models or anything, helped me handle low volumes of data. And so for the stress analysis portion, if you can only make like 10 samples, then Bayesian statistics is like a great tool that works better than t-tests, for example, for characterizing uncertainty.
That's for sure. And Jonah in the chat is asking, what improvements to the format can you imagine in the future? We are indeed thinking about supporting InferenceData format in our new posterior R package.
Yeah, so I think to the format itself, we ask anyone to come in and provide feedback. It's not like our format. We'd like this to be a format that anybody can go in and talk about. Like in the main chat, I put the specification that's up there right now. But like there's a planned features section, which has some more information about what everyone can do. But I'd say the biggest thing just is cross-language support. So NetCDF, which is what InferenceData serializes to, is completely language agnostic. It's actually not even a Bayesian format. It's an open science format. So if folks in the STAN community or in the Rainier community or you know literally any language, not Bayesian language, but like computer programming language, decided to use InferenceData, that just expands the number of people that can interact and share posterior samples and all of that.
And I guess that brings sort of like the last question. If people want to get involved in the project, what is the best way to do so?
Yeah, so we're a NumFocus project. So all the STAN is also NumFocus affiliated. So all the cool open source good vibes that you get from being in NumFocus, we have the same one. So just join the GitHub, and on there we have like a Gitter channel, and you can post in the issues. Just swing by.
That's fabulous. So there you go, folks. You can and hey, Vianey. So once Vianey comes into full mode, then we can proceed into the next one. But Ravin, that was very, very useful. Thank you so much for your talk. And on behalf of STAN and the STAN community, thank the contributors who send the talks in multiple languages. So thank you so much.
Yeah, thank you for making this whole thing happen.
Excellent. Thank you so much. And with that, I'll leave you all with Vianey, who will present the next speaker.
Hi, so next up we have Edwin, who talked about orbit probabilistic forecast with exponential smoothing. Hey, so you're muted right now.
Oh, sorry. Can you hear me?
Yeah. So yes, if anybody has questions, there's the Q&A. I love the shirt. Very appropriate for today. So yeah, so I guess I'm really curious how Uber uses Bayesian statistics, and is there a Bayesian team at Uber?
Oh, so we don't really have a centralized Bayesian team, although we have a lot of Bayesians in the company. But we do have like a regular meetup about the probabilistic modeling to share thoughts on different application of Bayesian models.
Okay.
Yeah. And the usage of it is like there are many different places. I think I could talk about the use case for my model. So mainly this is like forecast model. Yeah. So used in several areas, such as like by forecasting the future activities, we kind of we can make a better decision how we can like allocate the the supply and demand, and also like take a better like decision to facilitate the activities happens. Like if there is a search on particular events or holidays, something like that. And the second thing is that like because my model interpret some of the regression effect, so that we can like do a scenario simulation. Again, like we can understand like the impact of the holiday, and as well as like other types of like investment. Like for example, like how do we does our marketing impact for a certain unit, something like that, and then we can like make a better budget allocation.
Yeah.
So that those are the main usage of my model. Yeah.
That's amazing. So we have a question from Jeff. So how do these methods perform? You know, you're talking about forecasting, and we're in a pandemic, right? So how are these forecasting models, and how do they perform with unexpected market disruption, like COVID?
Yeah, that's a good question. So I think it really depends on the dynamics. Some of them it change not only like a shock on like a levels, but like the trend. So for that things, it is more challenging. While if that is like a sudden shock, and then it kind of recover gradually, our model is able to pick up such changes. So
that's great.
So I think it really depends. We do have some back tests on some data sets with COVID. It gives us more challenges, but it doesn't perform that bad.
Yeah. Oh, okay. Yeah, I bet there'd be a lot of people that hear that would be interested in learning more about that. So let's see, Vishvi, how does your method compare to deep learning-based methods, such as LSTM?
Yeah. So I think LSTM come into play for the like a more like a big scale of data. So our package mainly for right now mainly focus on small data. So like if you have like maybe like a 1,000 rows of time series, 1,000 time series set, or maybe a few 100,000 is okay. But I think LSTM is definitely target for like a bigger scale. Yeah.
Okay.
Yeah.
Yeah. Okay. Jonah asks, how does this package compare to Facebook's profit page, which I know you talked about in your presentation?
Yeah.
And he also says, nice StanCon 2009 t-shirt.
Yeah. Thank you. Yeah. I like Stan. That's right. Yeah. So I think the key difference for Profit and our package is that Profit used like a change point as a latent variable in the model, which kind of say you kind of saying that once you sample the change points, your trend is deterministic, meaning that you don't need to sequentially sample your latent variable. While our package is more traditional, following like the state-space model, that you have to sample your latent states one by one. So our model, in that sense, is is closer to like ARIMA, Kalman filter, that type of model.
Yeah. Thanks. Raul asked, how do you incorporate your own market actions, your policy from Uber into forecasting?
Well, that is more into like like how do you want to encode the variables into like a regressor. So if it is like a policy change, it could be like a binary indicator. If like a new X that maybe you have the clicks or impressions or span, then you can put it as like a continuous variables.
Yeah.
Yeah.
Okay. Okay, so I know you talked about this as well. So you have the Orbit paper, I believe. Yep. What is the timeline for releasing Orbit to the public, if it's going to be on a GitHub page?
Yeah, that's a great question. Yeah, we originally planned to have it done before this meeting, but unfortunately we are slowing down of the progress. But definitely it is on the roadmap. So we expect to have this open source project done on the end of September. So meaning like we will open source our code in GitHub. Yeah.
Okay, and so then is that when you expect other people are going to be able to contribute as well to the Orbit?
Oh, definitely, yeah. Yeah, so we will by that time we will provide a guide how the future contributor can like put that change, like suggest the changes for our code. It is very welcome for everyone to follow the guides. Yeah.
Yeah, it's awesome. Orion asked, have you looked into using approximate leave one out cross validation to assess the predictive accuracy of the models? Do you plan to
Yeah. That's a great question. Actually, I noticed there are some work from the maybe from the Stan developer or some article there. Like you mentioned, there is a specific version of linear cross validation for time series model, and it catch my attention. So at certain point, I was thinking to implement something similar, but turned out we don't have that package, like the LO package in Python. So that creates much more effort for us to replicate things like that. We are very happy if there are such a package, then we are very happy to provide an interface to that. Yeah. So definitely one of my consideration, but we want to focus on like the model do the forecast modeling while waiting for someone to create this kind of interface.
Yeah. So it seems then once you put it up on GitHub, you can publicize it in the discourse.
Yeah.
That's when people hear about it. Yeah.
Yeah.
That sounds great. I guess there's an opportunity for someone to do the interface then.
Oh yeah.
Yeah. We'll do one last question and then it's time. How are the effects of different marketing? How are the effects of different marketing channels and actions represented in the model output? So the effects of the marketing channels, other parts of the company, how are they represented in the model output?
Oh, okay. Obviously, we need to have those data, which is challenging. So I think that's part of the reason we have the we bring in this latent variable into the model.
Okay.
Yeah, that's hopefully can capture all the temporal effects, such as the marketing from other company, and also maybe the economics and political environments.
Yeah.
So
cool.
so yeah. In the ideal world, of course, we want to have all this sort of data, but it's probably not very realistic. So that's why that is that we have a compromise to have this model to kind of do our best to find the causal inference of the things we interest.
Yeah. Yeah. Well, we look forward to seeing that on the discourse whenever it's available, and then people can find you afterward as well, right? At the tables.
Yeah.
If they have questions.
Mm-hmm.
Well, thank you, Edwin.
Okay. Thanks.
Right. Okay. So next up, we have Ryan Giordano. And I'm quite excited for the questions here as well, because it's effortless frequentist covariances of posterior expectations in STAN.
Yep.
So welcome, Ryan.
Hey, thank you. You have some hard questions prepared for me.
Yeah, so we do have, of course, if you have any questions, please ask in the Q&A. We're talking about frequency properties and asymptotics here as well as distribution, so it's a fun mix. And of course, so we've chatted before, but I wanted to sort of ask you, we're talking about comparing these frequentist and Bayesian covariance matrices. And you talk about the small misspecification, but why isn't it, I guess, what is it practical about these differences from a Bayesian and a frequentist framework? Why is it practical to understand that they are different?
Yeah, that is the question, and look, I'm going to be honest. I don't think I have a good answer for this. This is a bit of a work in progress. But the first thing that I should say is that the Bayesian covariance and the frequentist covariance are different, right? No matter how big your N is, if you have enough MCMC samples and you can evaluate the posterior covariance accurately enough, they're different, right? So in this sense, the test that I did at the end of the talk is, it's a little shaky, because if you had a small enough Monte Carlo standard error, you would reject everything. So I kind of regret doing it that way, but it was too late to redo my video. So thank you for asking this. What you really care about is whether they're different to a practical degree, right? Whether the Bayesian covariance is, for example, 50% larger, 75% larger than the Bayesian covariance, which would indicate a material misspecification. It indicates that there's something so wrong that your covariance matrices are probably not good, right? And so just testing whether they're actually different, statistically is not important. What matters is whether they're practically different, right? So that's the key point that I'm glad you gave me the chance to clarify.
Yeah, okay. So Martin asked, I really enjoyed your talk. Thanks, very cool. Did you find any interesting examples of misspecification when running the bootstrap and infinitesimal jackknife on the ARM models?
I did. There are a number of the ARM models that are evidently misspecified. And I have to apologize that I wanted to dig into them before this talk, and I just did not get the chance. I spent a lot of time preparing to very carefully answer the question that Vianey just asked before. So I have a ton of graphs that I can show you about that question at the table. Yeah. I didn't get to dig into them, but yeah, there are some. Now, I mean, I should say, like, it's a famous textbook curated by the experts in the field, so most of them are fine. And what I would really, really like is to spend time digging into models that people actually care about, right? Rather than these textbook models. So my dream outcome for the STAN conference would be if people like come to me and are like, here's a data set, would you like to try this and see if you can detect misspecification and diagnose it for me? And maybe you let me use it in my paper. That would be amazing. So no, I'm sorry, I didn't dig in. Yes, there is misspecification. I can show you some graphs at the table if you want to come, but I don't know why. I can't tell you any more than that.
Yeah, well, it sounds like a fun challenge.
Yeah.
So Hyunji, could you give some example cases or conditions where the results of frequentist central limit theorems and Bayesian central limit theorems might differ? Thank you.
Yes, that is. You obviously watched the talk because I asked you to ask that. So thank you so much. I had really high hopes that the example I'm going to describe would have worked with the method. And a couple of weeks ago, I tried it and it didn't work. And it took me like a day to figure out why it didn't work. And it's really interesting. So imagine you've got a logistic regression model with a bunch of random effects. Say you've got an advertising model and you either click or you don't. And you've got like 1,000 individuals, and each one of those individuals has a latent propensity to click or not to click. Let's call those lambdas. So you've got 1,000 lambdas. I suppose you're actually interested in the variance of that random effect, but you don't want to fit a really expensive prior distribution, or you believe that your prior distribution is misspecified. You want to use a gamma or something, even though you know it's multimodal, right? Mm-hmm. Well, one thing you can do is you could ignore the fact that your prior is misspecified and look at the sample variance of your fit lambdas, right? That's a posterior quantity that you can get. And because your prior is wrong, that posterior variance is wrong, right? This is a case where you might want to look at the frequentist variance of the average of those individual random effects. The problem with that in the infinitesimal jackknife is each of the covariances for those individual random effects doesn't obey a Bayesian central limit theorem because you only have a few observations per individual. So even though when you add them all up, that average does obey a Bayesian central limit theorem, individually, the covariances that comprise the infinitesimal jackknife don't. And so you get a screwy answer. So it's really interesting to ask whether you can fix this, right? There are all these old saddle point methods for like using central limit type things with small data. Super interesting to look into, but that's the kind of thing that you can't do, right? Where you have something that obeys a Bayesian central limit theorem because you're adding up a bunch of little individual random effects that don't have a lot of data per random effect. So they don't each obey a central limit theorem. You can't add them up and use the IJ. So it's too bad. I thought you could, but you can't.
Yeah, okay.
Yeah.
Okay, so there are some comments, not questions, that I'll say. It's a frequentist baffled by Bayes, Jeff Hubert. Thank you for your helpful comparisons. So this is something that's near and dear to me. Is when you encounter misspecification, did you encounter multimodality? And I'm going to think of it as the likelihood function.
All right. Yes. No. This technique will not deal with multimodality, right? And I think it shouldn't. I think, actually, I have kind of strong feelings about this, so it's going to come up. I think frequentist notions of uncertainty about multimodality are basically broken, right? Because the frequency with which you find a particular mode is basically a function of the optimization algorithm you use, not of any basic statistical properties of that mode, right? So it'll depend on whether you did trust region versus BFGS. It'll depend whether you did a uniform initialization or a hot start from something else, right? And that means nothing, right? So when people do stuff like bootstrap a posterior to deal with uncertainty over multimodality, that result, I'm sorry, it just doesn't mean that much, right? Now, Bayesian statistics is also broken with multimodality, right? So you can use Bayes factors to compare the relative probabilities of different modes if you can calculate it. But there's this thing called Burke's paradox, where if there's actually any real uncertainty between the modes, that uncertainty is super unstable to frequentist sampling. So I don't know, I'm like a noob at this stuff. I don't know what the solution is to proper uncertainty quantification over multimodality, but this is not it. The infinitesimal jackknife works on one mode. It gives you the uncertainty around that mode. That's all it will ever do. That's all it's even designed to do. So yeah, no, it won't work for multimodality. Nothing works for multimodality. I'm sorry. Yeah. That was a little pugilistic. Come to my table and argue with me.
Yeah, I mean, yes, I definitely agree with you on the multimodality stuff. So,
yeah.
You asked one more question. Do you also make use of cross-sectional covariance of each posterior expectation when computing their temporal covariances?
I don't think I know what that means, and so probably not. Bishop, I don't know, Vianey, do you understand the question? Or Bishop, do you want to clarify?
Maybe we could just leave it here and invite Bishop here.
Yeah. I'm sorry. It's my fault, not yours. Yeah, sorry.
But yes, no, thank you so much for your presentation. It's great. I love asymptotics as well. So it's always fun to think about asymptotics. I think if I had one more question to ask you, it would be about pre-asymptotic behavior.
Yeah.
Right. So we're throwing around all these asymptotics and how we're comparing them, but really there are a lot of cases where it's not going to hold.
Yeah, that's right. So the first thing I want to say is, like, I think with frequentist statistics, there's kind of like no game in town except for asymptotics, right? You have permutation tests if you actually care about decision making. But if you don't know what the power of those tests are, it's hard to do inference, right? So if you don't do frequentist inference, you're kind of stuck with asymptotics. That having been said, I feel like I'm doing asymptotics reluctantly. What you might actually care about is the effect of actual perturbations to your data set, right? In other words, there's a sense in which, for example, if you're doing cross-validation, what you care about is not the limiting bias or the bias if you actually had true, this expectation undersampling to the real thing, but what actually happens if you take one data point out? What actually happens if you take 10 data points out? And if you ask those types of questions with tools like the infinitesimal jackknife, it turns out you can actually bound these errors in finite sample. And so we have some frequentist work called the Swiss Army infinitesimal jackknife that does some of this. With Bayes, it gets a little bit tricky, largely because you're conditioning on your MCMC samples. So like what it means when you condition on your MCMC samples and ask for finite sample quantities ends up being like you're doing different approximations to the importance sampling distribution. And that maybe isn't what you actually want to do, but there's some angles there to talk about. Again, maybe that's a table if people are interested.
So if anybody has any other questions, want to chat about frequentist covariances, we can all go to Ryan's table. Cool. I believe we are close now to being done. We're going to have a virtual coffee and poster session soon, and we'll be moving back to the network space.
And so I just have a couple of closing remarks just before jumping into the tables. So thank you everybody who registered for the conference. We are really stoked about how many people register online, and running it through 24 hours would not be possible without Sally and the kinetics team. So kudos to Sally and her team. To our sponsors, Metrum, Hoxo, General, Jumping Rivers. Thank you so much, everybody. and time for coffee, and or I guess like whatever time zone you are, grab your favorite beverage, and I'll see you at the tables, everybody. Thank you.